Hello, good afternoon, good morning, good evening, whenever you happen to be watching this video, and welcome to Lecture 2, Part 1 of ENGR 2301 Engineering Statics. So, in this portion of the lecture, we are going to really start looking at vectors. And this may be something you have seen before in previous coursework, but we're going to review and start at the basics here and build on it as we go. So we're going to talk about in this portion of the lecture looking at what a vector is, what the difference is between a vector and a scalar, and some of the places that we may use these, some examples of each. So let's look at a vector and a scalar. So vectors and scalars are both examples of ways that we classify quantities or measurements. So let's create a little table where we explore both scalars and vectors. Let's say scalars and vectors. Let's compare and contrast them. So let's take a look here. So both of these are used for measuring quantities or measuring things or measuring. When I say quantities, these can refer to a variety of different things that one might measure. Everything from force to electric field to energy. Most of the things that you physically can measure are either a scalar or a vector. In fact, I'd be hard pressed to think of an example of anything that is actually capable of being measured. And if you can assign a value to something, it's either a scalar or a vector. And it'd be hard to pick an example of anything that's not one or the other. I can't think of one off the top of my head anyway. Okay, so scalars versus vectors. First of all, a scalar is a quantity that has only magnitude. A scalar is going to have only magnitude or size. Only magnitude, and of course when we say magnitude we mean size, or I should say but no direction. However, it can be positive or negative, but it can't have a direction, like an angle associated with it, etc. Vectors, on the other hand, will have both magnitude and direction. So vectors will have both magnitude and direction. So what I mean by this is, if I were to go, say, let's look at the difference between, say, speed and velocity as a classic example of a magnitude or a scalar versus a vector. So speed is a scalar quantity. It has only size. It doesn't have a direction. If I say for speed, for example, speed is purely a scalar quantity. It just says, for example, I travel 60 miles per hour. Velocity, on the other hand, is a vector quantity. It's a vector quantity, and because it's a vector quantity, it's going to have both magnitude and direction, and I might say something like 60 miles per hour east, or 60 miles per hour north, or whatever it might be. There is some directionality associated with this. So again, we can see the very basic idea here that scalars have only magnitude and vectors have both magnitude and direction. What else do we need to consider in terms of scalars versus vectors? Let's see, what else do we want to know? Scalars versus vectors. Here, let's talk about how you can add them together. Scalars can simply be numerically added. If I'm talking about going in a straight line, or if I talk about something like electric potential, voltage, that sort of thing. If I add the potential between two things, I can simply, if I add two different point charges are producing, say two different point charges are producing potentials at a point. If one is producing a 20 volt potential, another is producing a 40 volt potential, I can simply add those together. Or something like distance. If I'm traveling in a straight line, if I'm confining motion to a straight line so that distance can be avoided, if I talk about speed, if I'm traveling in a straight line, if I first am traveling at 20 miles per hour, and then later I accelerate an additional 20 miles per hour, well then my final velocity is 40 miles per hour, or I should say my final speed is 40 miles per hour. Is 40 miles per hour. As long as the speed, or as long as all of the displacement, as long as I'm traveling in a car, or yeah, I guess a car would be the most likely example there, or a train or something like that, as long as I'm traveling in a perfectly straight line, I can simply directly add speeds together like that. But the minute I start traveling in turns or traveling different directions, that's when I can no longer apply this very simple, straightforward summation. Or if I didn't care about direction, if I was concerned with something called distance traveled, for example, distance traveled. If I say I traveled 60 miles east, and then let's say I first went 60 miles east and then 20 miles north, well, the total distance I walked or drove or whatever is just 80 miles. Its displacement would not be 80 miles. We'll see that over here. But it is still, if all we're concerned about is total distance traveled, you can simply sum them up numerically. 60 plus 20 is just 80 miles total. If we don't care about direction, we can simply sum these together. But vectors, on the other hand, cannot simply be summed numerically. They need to be summed either in components, graphically, etc. They need to be summed usually on a coordinate plane for 2D vectors, or in 3D space for 3D vectors. So for example, if I go to something like this, let's say I travel 20 miles, let's say I have two different velocities that I want to add together. There is 20 miles per hour maybe to the east, and 20 miles per hour south here. And the resultant of these, and we'll look at this more in the next video when we start looking at vector summation, the net velocity, or the combined velocity of both of these vectors, would be not the numeric sum of 20 versus 20, but the Pythagorean, the hypotenuse. The resultant v would be, let's say that would be the square root of 20 squared plus 20 squared, and let me throw that into a calculator here. That's just very basic geometry. Let's get this, the square root of 20 squared times 2. That is 28.3 miles per hour. 28.3 miles per hour. And we could do something similar if we looked at displacement versus distance traveled. So let's look at some examples of both scalars and vectors. Some examples of scalars and vectors. So examples. And we could really spend all day writing about these and coming up with different examples and things, but there are innumerable examples of both scalar and vector quantities. So let's look at scalar and vector. And we've already seen some of these. So let's talk about simple length first, length dimension. If we talk about distance traveled, that would be a scalar quantity. If I'm not concerned about what direction is being traveled, I'm just talking about the total distance a car travels, or the total length of a track, or whatever it might be, then distance travel is important. If I'm talking about the distance as the crow flies, or the actual vector along a plane, then that would be displacement. You remember from physics class and geometry, etc., that displacement is final position minus initial position. It's basically x final minus x initial on one-dimensional motion. Or if you have a 2D plane, for example, or let me just go ahead and even extend this to a 3D case. In the case of a 3D motion, it would be delta x squared plus delta y squared plus delta z squared. maybe not too important for what we're looking at here, but can be useful as an illustration. Okay, then let's talk about motion. For scalar, we would have speed, but then vector, we would have velocity. Velocity would have some direction associated with that. You could talk about velocity east, north, south, west, up, down, forward, back, whatever it may be. But velocity, if it's going to be a true velocity, is going to have some directionality associated with it. And then I could have acceleration. Now, generally we don't talk about, we could say the magnitude of acceleration, but generally we don't talk about acceleration having a scalar equivalent. Usually I think of acceleration as purely a vector quantity. Let's talk about something that exists only as a scalar quantity, though. Think about energy. When you learn basic Newtonian physics in physics class, when you hear, say, an energy measurement of 12 joules, well, in certain illustrations, certain examples of potential energy, like gravitational electric potential energy, you can have negative potential energy, but you don't have 12 joules at an angle of 20 degrees above the horizontal, or 12 joules at an angle 20 degrees north of east, or something like that. Energy can have a positive or negative sense depending on how you're defining it, but it cannot have a direction. It is purely a scalar quantity. It's not going to have any kind of directionality associated with it. It's a scalar rather than a vector quantity. Same thing with electric potential, like electric potential energy, or electric potential that's just dividing that by coulombs, etc. And I could also have things like momentum is a vector quantity, both linear and angular. Angular. And the really big one and the really big set that we'll see in this class is mass and force. Mass is a scalar quantity. Something does not have 12 kilograms of mass upward or 5 kilograms of mass downward. It just has 5 kilograms of mass. Mass is a scalar quantity. Force, on the other hand, is always going to have a direction associated with it. We have 2 newtons to the left, 3 pounds downward, 5 newtons at an angle of 45 degrees above the horizontal, and 3 degrees above the x-axis, or something like that. There's always a directionality associated with force. And that really is the basic difference between scalar quantities and vector quantities. And we need to handle these fundamentally differently. And most of the time in this class, we're going to be working with vector quantities because they really do have more effect of how forces distribute through bodies. And a lot of statics, or potentially even most of statics, really is studying how forces distribute through systems and bodies and frameworks. And so it makes sense that because force is a vector quantity, we're going to work with vector quantities in this class a lot more than we'll work with scalar quantities. So let's talk about a few terminologies, or a few bits of terminology and nomenclature that you might want to know in case you haven't seen these. Well, you definitely have seen these by now, but maybe it's been a while since you took calculus or physics, and it would be good to do some basic review. So terminologies, first of all, magnitude of a vector. The magnitude of a vector is its size. Size or scalar equivalent. So if you have a vector that has an x component and a y component, its overall magnitude is its overall length along the hypotenuse here would be its magnitude. This would be its magnitude here. And the way we indicate that in written form, if I have vector A, the magnitude of A is written as follows. I would write that as, we'll first need the vector sign above my A, and I'll put a double bar around it to indicate magnitude. And when we get to components, later on we will look at how to actually calculate this from, say, components. But we'll see that later in the lecture today. But I just want to go over some of the symbolism here, or symbology, or nomenclature, or whatever you want to describe it as. So that's the magnitude of a vector. Next, I want to describe a vector's line of action. We use this term a lot, especially when we get into force balances and things like that, so it would be useful to actually define this. Line of action. Well, it's kind of in the name, but the line of action is the imaginary line along which a vector acts. Line through space which a particular vector passes through. Or maybe lies along. It goes backwards and forwards to infinity. The line of action goes backwards, or is of infinite length, I should probably say. It's not a line segment. It's if you remember back to your grade school geometry, the difference between a line segment and a line was that a line reached off to infinity forward and infinity backwards. A line segment was of a fixed length. So, and that applies here. A line of action is a true geometric line, so it has infinite length. And so the reason this is important is that consider, for example, a rigid body. Maybe a center of mass here. What happens if I apply a force to its surface? Let's say I apply a force to its edge here. This would be like a planar rigid body, a pancake or something like that. If I apply a force to this body, well, here is its line of action. The force itself does not, now the force would be carried by the rigid body, would be passed into the body, but the force itself, if I'm just standing out here, if I'm floating in space standing out here, I'm not going to feel the effects of this force. If I was in contact with it, if I was standing here and had my hand here, I might feel the effects of this force being passed through the body. But if I was just standing here, as long as I wasn't in physical contact with this object here, I would not feel any effect of that force. The force itself only affects the body that it is in contact with. But its line of action, if I was standing here, its line of action would still be passing through me. A line of action, the effects of the force itself terminate on whatever objects it's in physical contact with, but the line of action extends backwards and forwards to positive infinity and negative infinity. And that is a good idea for the definition of a line of action. Okay, so that's just some basic terminology, and I think that'll serve as a brief introduction to scalars versus vectors and some useful terminology involving them. In the next portion of the lecture, we'll look at some basic ideas of how to work with vectors, including some very basic vector addition principles. All right, that'll do it for now, and I will see you soon in part 2.